Hello everyone, and I hope you're all doing very well. Today I've got a wee treat in store for you. I'm going to show you a video on electrostatics or static electricity. This is a phenomenon we're all familiar with. If I ever touch anything metal, under certain circumstances we can find ourselves getting a wee tingle or a wee shock, and we say, that's static, and that would be quite right to say that. What is going on though? What I'm going to do is I'm going to show you a small number of short videos illustrating the phenomena. Then what I'm going to do is I'm going to show you the exact same videos backed up with an animation to explain what's going on. Hopefully you will understand it well enough to take the concept further, and if you come across another phenomenon in electrostatics, you will be able to explain it successfully using the short sequence of videos that I've shown you. I hope you enjoy the video just as much as I enjoyed making it. Not just making the wee films, but making up the wee animations that go along with them. I'm now going to hold the rods next to the hanging bob and we'll see what happens. And then I'm going to hold the rods just above the small pieces of paper and we'll see what happens. Well, nothing happened. So what was the point of that? So what was the point of that? Well, you'll be wondering, well, what are these cloths for? What are these cloths for? Now I'm going to give each rod a rub of these cloths and repeat the experiment, and we'll see what happens and take a note of it, if indeed anything does happen. Well, clearly something happened there. The rods attracted the paper towards them, and the rods attracted the hanging bob towards them, all except the metal rod. We'll need to explain that later, which you might find that a wee bit odd, because after all, as I said earlier, it's when you put your finger near something metallic that you get a shock. But the rods and the paper did not seem to interact with each other. It's best when we're doing these experiments to use the language of physics, and the language of physics here is force. And what we say is this, what we can clearly see is this: the rods exerted a force on the paper and on the hanging bob, and the bob and the paper was attracted to the rod, and we call that the force of attraction. I'm now going to rub the polythene rod, put it on the upturned watch glass. I'm going to rub the acetate rod, bring it up to the polythene rod, and we'll see what happens. Then I'll repeat the experiment with two polythene rods that have been rubbed, and we'll see again what happens. now we can see an interesting thing. When I brought up the acetate rod, that pulled the polythene rod towards it, and you can see it rotating. When we brought up the polythene rod to the polythene rod on the watch glass, then we saw a force of repulsion as it pushed it away. So now when it comes to electrostatics experiments, we've got forces of attraction and forces of repulsion. Now I've wrapped the pendulum bob in tin foil. Then I'm going to bring up a rubbed polythene rod. I'm going to allow the rubbed polythene rod to touch the pendulum bob, then I shall withdraw it. Now you're looking for forces of attraction and forces of repulsion. Remember, a repulsion is a push and an attraction is a pull. In our case, so what's doing the pushing and pulling and what's being pulled and pushed are not in contact with each other. That's an important point to observe in these experiments. I rubbed the polythene rod, brought it up to the hanging bob, as we would expect. The hanging bob went towards it, but then I allowed it to touch, and then I withdrew it. And when I brought up the polythene rod a moment later, the polythene rod did not attract it, it repelled it, it pushed it away. That's interesting. When I brought up the acetate rod that had been rubbed a moment later, the acetate rod did not push it away, it attracted it. It was pushed away by the rod that touched it earlier. Isn't that interesting? We'll return to that. Now I've got two pendulum bobs, both wrapped in tin foil and both hanging, and you can see they're both in contact with each other. Well, I'm going to do the same again. I'm going to bring up the polythene rod that's been rubbed. I'm going to allow the polythene rod to touch the two hanging bobs. Then we'll simply see what happens. Then we'll get down to explaining the phenomena using a theory that we know. And you can see for yourself what happened there. As soon as the two pendulum bobs were touched with the rubbed rod, then they separated. They pushed each other away. That's a repelling force. Until I touched it. As soon as I touched it, then everything went back to normal. Now it's time to explain. If we could peer deep inside these rods, the metal rods or the non-metal rods, we'll come across tiny wee structures that we call atoms. An atom is tiny. It's actually of the order of 1/10 of a nanometer. Now imagine a nanometer. What you do is this. Imagine you've got a ruler. Look at the 1 millimeter space. Divide that 1 millimeter space a million times and look at that space. Tiny, too tiny to imagine. That's what's meant by a nanometer. If you take that nanometer space and divide it a further 10 times and take one of those divisions, then we have 1/10 of a nanometer. That's the order we're talking about here. That's the size we're talking about here. Too small to imagine. Some people ask me, well, how do we know that they're there if they're too small? Well, it's because of experiments like this that we need to explain. And it's because of our observations. It's because of our deductions. It's because of our inferences that we can deduce the structure of the atom and its inherent properties. And when we do that, we can more than adequately explain the phenomena that I've just been describing. The colour coding is just for convenience, and the symbols on the particles are just for convenience. I've got a grey particle, I've got a red particle, and I've got a blue particle. We need to consider only the red and the blue. The red particles, along with the grey particles, consist of the nucleus of the atom, right in the centre. The blue particles are called electrons, and they're going round and round and round and round. The red particles, incidentally, are called protons. Notice the red particles have got a positive sign on them, and the blue particles, the electrons, have got a negative sign on them. This is referring to a property of these particles, and we call that property charge. This simply means that if you've got two charged particles close together, they will interact with each other. In other words, they will either exert a pulling force on each other or a pushing force on each other. Then we know, if we observe that phenomenon, we know the particles are charged. So when our charged particles are attracted to each other, and when our charged particles repel from each other. Remember, an attraction is a pull and a repulsion is a push. Look at this diagram here and see if you can work out yourself what the rule is. The two positives repelled each other, the two negatives repelled each other, but if the signs were opposite, a positive and a negative, then they attracted one another, and that is the rule. Sometimes we state it like this: unlike charges attract, like charges repel. And that's a rule you should never forget in this context. Let's explain the spinning rods. Atom has the same number of positives and negatives. Therefore, a rod will have the same number of positives and negatives, and we say it's electrically neutral. And that tends to be the case under normal circumstances. But we can change that balance. We can take a cloth and we can rub off negatives onto the cloth from the rod, leaving the rod with a positive, a net positive charge. Or alternatively, we can rub electrons off the cloth and onto the rod, leaving the rod with a negative charge. You'll have noticed the metal rod did not interact with the small pieces of paper or the hanging pendulum bob. This is because metals and non-metals have different electrical properties. We label non-metals insulators, we label metals conductors. The rods that were rubbed did not change shape, so we can infer that the atoms that make up these rods are fixed in position. It's not the atoms that move during these activities, it's only the electrons that can move. They move from the cloth to the rod, or from the rod to the cloth, depending on what cloth and rod we're using. The metals have got an interesting property. We find that it's very easy for the electrons to jump from atom to atom and swap places. Therefore, it's easy for electrons to move through the metal structure. And because it's very easy for electrons to move through metals, we call metals conductors. Now, what happens therefore if we rub a metal rod and we put electrons on? Well, the electrons will simply repel each other, they'll push each other away. And it's very easy for the electrons to get away from each other because they're in the metal. So they'll pass through the metal very, very easily and to whatever the metal is attached to, leaving no net negative charge at the point you rubbed. Therefore, we don't see the effects of attraction and repulsion. Unlike the non-metals, the insulators, if we put a charge on an insulator, then the charge will remain at the point we put it on. And although the charge will push each other away, certainly, they can't get away from each other. because they're a non-metal, and non-metals do not allow the conduction of electrons very, very easily. You'll have noticed that the charged rod attracted the pendulum bob towards it, even though the pendulum bob had not been rubbed and therefore did not have an overall charge. This is because when we brought up, for example, the negative rod to the pendulum bob, the negative rod would have repelled electrons to the side of the pendulum bob furthest from the charged rod, leaving a net positive charge at the side of the bob closest to the rod. Therefore, the force of attraction was greater than the force of repulsion, and the rod attracted the bob towards it. And it's a similar argument for the paper. That is called polarization, where we haven't changed the number of charges, but we have separated them to a positive side and a negative side. And the final one was charging by contact. When I brought up the negative rod, for example, negative rods jumped off the rod and onto the silver paper, and they spread themselves around, and we could see the effect. Yeah. So what is meant by an electric shock? Well, quite simply, see if a great deal of electrons are either entering or leaving your finger at a very, very high speed. That means a lot of energy is entering and leaving your finger, and you will sense that as a shock. Now, when it comes to something metal like a door handle, a metal like a door handle can build up charge in a variety of ways. Rubbing, touching, and polishing, for example. If you've got a great deal of electrons on a metal handle and they're all close together, but they're pushing each other away as much as they possibly can. And the more you put on, the greater the force they push each other away with. But they've got nowhere to go. But they do have a great deal of pent up or potential energy. So when you come along and touch it, the energy, the electrons with their high speed enter your finger, and you can feel that as a shock. Thanks for watching Young Scottish Physicist.